Okay, but will it be the same file, or will it be? Okay. Okay. All right. Thank you. Bye-bye. All right. The first part of the semester up to this point was really sort of learning the lay of the land with regards to the ASP.NET framework. All right. Just about what dynamic pages are, how they are generated on the server, and specifically what are some of the tools that we have available to us in ASP.NET to make those things work. And then we examined some specifics, and did some form processing and so on and so forth. Really, our next big task is to sort of marry what we know about the ASP.NET controls to database stuff. That's kind of the main event of the class, right? Web database integration, so we're going to do that. But first, we're going to spend some time reviewing databases. How many of you have had CISS243? That's the database class. So 2 out of you have as well? A while ago? Okay. When did you have it? Can I ask, did you have me? Okay. All right. So, we are going to spend a little bit of time review, and one of the things I'm going to do is we're going to sort of play it by ear to see how much of this review you need. All right. It's rare in this class to find a database expert, so any of us can use a bit of a review, but just how much, that's what we're gonna try to determine. The big thing with databases, as it is with, I stress in all my classes, is the notion of getting the design right. Okay. It's sort of a fact in the world of information technology that the kind of data and the structure the data stays pretty constant over time. If you can imagine building a database for Lorain Community College now versus 40 years ago. What would 40 years ago have been? 1970 something, right? 72. All right. If you could imagine building a database then versus now, let's think about what would be different. Would it be different? There would be students. All right. Well, there were students then too. There would be teachers. Well, there were teachers then too. There are classes. Well, there were classes too. There were different sections for a class. Yeah, well, there's that too. There's day classes and night classes. Yeah, there was that too. There's adjunct and full-time professors. Yeah, there's them too. There's buildings with rooms. Yeah, there are too. There are degrees that people will earn at some point. Yeah, there are too. Really, if you think about it, there probably isn't anything different structurally in the database now versus then. And I thought of something, but I immediately am correcting myself here. I might say that it might be different because there are distance learning classes now. That might be a difference. However, they had TV classes back in the 70s, I'm pretty sure, where you would watch it on Channel 25 and then, come in and take a test or whatever. So there were even, if you were a sharp enough database designer, your design might have even accommodated different delivery methods, of which the internet is the newest one. You might not have anticipated the specifics of a web class, but you would possibly identify that there are more ways than one to deliver a class. So the idea is that the structure of the data really doesn't change that much over time. The way people use the data changes drastically. All right. A lot of people now are really into analytics. Let me try to pull up an article that I just saw over the weekend. I think it was over the weekend. As that's bringing up, but the way people are using it is different. There also is, due to electronic means of capturing data, there's a greater ability to capture data than there has been in the past. In the past, stuff would have been manually entered into the computer. Now, you have those RFID tags, and you have all sorts of things and all sorts of ways of getting stuff in, capturing that data. All right, here's the article. They call it the age of big data. All right. And it's easy enough to find if you want to see it. Just Google New York Times big data, and you'll be able to find it. And it talks about it. There's people mining information, or data rather, from social networking sites, Twitter, to get a sense of how their company is being viewed. All right? Do keep in mind that data is just the raw facts, though. That has to go through some processing to produce some sort of what we call information, or something that is capable of giving us some sort of insight and capable for us to take and take some sort of action on it. And I think that's really the point of that article, is yeah, we got a lot of data, but do we have the people with the insight and the wisdom and the software to assist in that, to be able to derive some sort of insight from that? At any rate, the point is that the way the data is used changes frequently, the way that the structure of the data doesn't change. For example, no one envisioned that you could probably go and schedule yourself by computer in 1972. But if you look at the structure, the data structure of a schedule, it's the same then as it is now. As with most things, the design is critical, all right, for a couple reasons. First of all, as we mentioned, the design doesn't change that much. The second thing is a phenomenon that people notice, and I bring it up in most all of my classes, and that is when you compare the expense to make a change in a piece of software versus at what stage you discover it. And I'm not sure if I showed it in this class yet. I show it in most every class. But the graph looks like this. And for you math fans out there, that has a positive first derivative, all right? The one thing that I remember from calculus, all right, which means it's increasing at an increasing rate. So it's not just increasing linearly, like this, in a straight line at a steady rate. It's increasing faster the further on you go. And what this graph shows is it compares the expense of making a change versus the phase of the project that you detect the problem in. And it goes up. The idea is if you catch a problem early in a project, when you're planning and designing, to change it doesn't take much. It might take some expense, you might have to rework something, but the change doesn't take much. As compared to when you're building the project. So this might be the design phase. This might be the build phase. This might be testing phase. And then finally, when the system is implemented. The expense related to making a change goes through the roof. And therefore, the moral of this story is you spend as much time as you can at this stage trying to get your design right. Because that's when it's easy to change. The analogy would be like an architect with a building. If the building only exists on a blueprint, it's easy to move walls around on a blueprint. All right? It's a lot harder to move actual walls around. All right? So design is critical, and database design is critical. The database sort of provides a foundation for the rest of the application. If the database is solid, the application can be solid. If the database has cracks in it and is not really designed well, then the rest of the application is apt to have issues. Let's be sure we define our terms to start out with. Does anyone care to offer a definition of database? Including the people that seem to like to walk across past the room every day at this time, yelling at the top of their lungs. Okay. Collection of information. That's a start. That's a good description. Stored in tables. All right.
With attributes.
With attributes. All right. All those are true. Let's sort of tighten it up a little bit and close the gaps. For one thing, databases contain information about multiple entities. Contains information about multiple entities. In the old days, you didn't have databases, you had file systems, flat files or even index files. And they would typically have their little silos of data. There would be an employee file that would have data about employees in it. There'd be a project file that had data about projects in it, and so on. The key thing about a database is it involves having data, and I prefer the term data rather than information, because information is something we derive from data, about multiple entities. So we will not have two databases, one with customer information and one with project information. We will have a single database that will contain information, will contain data about both. The other key thing about databases, and again, the tables that were mentioned, I'm using the word entity in this sense, but tables would be another good word to use. Typically, when we talk about designing a database, we talk about the entities involved. When we talk about actually creating the database, then we talk about the tables that get created. All right? The other thing that's key to a database is that in addition to storing the multiple entities, the different attributes, as was mentioned, all right, we store relationships between entities. Isn't that nice for Valentine's Day? The lecture will be in large part about relationships. That's beautiful. Now let's ponder the significance of that. What that means is that we can connect members of different entities. We can, in the database, make it so that the project points to the customer that that project is for. All right. In addition, we can do more than that. We can make it so that when you enter in a new project, you can't enter in a customer that doesn't exist. All right. That really was the problem with file systems, with flat files or index files even, is that you could potentially have these silos of data. You could have inconsistencies. You could have a project that did not relate to any existing customer. All right? Now you might say, how could that happen? Well, it could happen because programmers are humans and they make bugs. All right? And they introduce bugs into their code. Which means that the programmer might have had code to validate and make sure that you can't enter a project without a customer. But maybe somewhere down the line, a programmer slipped and allowed you to delete a customer without seeing if there were any outstanding projects out for them. Then, all of a sudden, you have a project floating out there without a valid customer. That's known as referential integrity. File systems, because everything was stored separate, and it was up to the programmers to write code that knew the rules and implemented the rules. As they say, a chain is only as strong as the weakest link. So your worst programmer determined how valid your data was. Because whoever threw in the most bugs, all right, is the one that broke it the most times and caused your data to be bad. Now, how do relational databases get around that? Relational databases get around that particular issue of referential integrity by storing not just the data about the different entities, but the relationships between entities, and the relational database enforces those rules. So if I create a project table that's connected to a customer table, and I establish what's called a foreign key between project and customer, if I point the customer number in the project table to the customer number in the project table, then the database won't let me create a project without a valid customer, or delete a customer if there's outstanding projects, or anything along those lines. All right? The database provides sort of a consistent checking of these rules, whereas it doesn't matter how bad your programmers are. They're going to have to figure out something else to screw up, right? Because they can't violate the referential integrity because the database has that covered. All right? And that really is the key benefit to relational databases versus flat files. The other big benefit is that because we're storing different entities together, as we said, a collection of things, collection of tables or entities, we don't have redundant data. So in files, since each file was sort of its own silo, we might have to repeat a little bit of data here and a little bit of data there and a little bit over here. And that would lead to potential inconsistencies and so on. With relational databases, everything's in one place, and if it's related to something else, it gets related via these keys, primary keys, foreign keys, and so on. So, let's define a few terms. And as I mention these terms, I'll mention maybe some commonly used synonyms that are used for them. All right? First term is table. Again, I already said a sort of a synonym for that is entity. All right? Usually you call it an entity when you're in design mode, and you call it a table when you're actually building the database. An entity is typically all the data about one thing in your system. Typically, entities are nouns. Persons, places, or things. Customer is well, I guess depending on the kind of customer, it could be a person, or it could be a thing, a corporation. Although, according to the Supreme Court, right, corporations are people too, so, all right, so I guess that would apply as person, all right. A project is not a tangible thing, but conceptually it's a thing, all right, and so on. So all the data about these are going to be stored in the table that's related to them, all right, and it's only going to be stored in one place. Attributes sometimes called fields, or sometimes called columns. Fields is sort of the old file term. When people use files, they talk about fields. All right. Are the different values about a member of that entity. I sort of skipped ahead one. One thing I missed is a row, or sometimes called a record. Again, that's a file term. And I think if you have a PhD, you call it a tuple. Let me look that one up. actually, this is, I mean, what if you have to have a PhD to follow this, all this set theory business. Actually, according to this, it looks like a tuple is an attribute. But again, who knows? I'll erase that. A row or a record is everything about a member of that entity. So for example, the entity or table would be student table. There'd be a row in the student table about each of you. And that row would be consisted of a series of attributes or columns that were the specific single elementary pieces of data about you. All right, your name, address, phone number, student number, and so on down the line. Primary key is something that uniquely identifies members of the table. When we say uniquely identify, it means that it identifies only one. All right? So, for example, in the student table, you could not have the phone number as a primary key. Why not? Well, there might be a husband and wife that both have the same phone number that are attending classes. So you could not use phone number because that would not uniquely identify a student. That would identify two students. And to be a primary key, it has to uniquely identify a member of that entity. The other restriction about a primary key is that every row in the table has to have a value for it. All right? That'd be another thing that would be wrong about trying to use a telephone number. It's possible there could be a person that doesn't have a telephone. You can't tell them, well, I'm sorry, you can't attend school then. You know? Oftentimes what's done is a key will be generated. And that's like what like a student number would be. That number doesn't really mean anything into itself. It's really sequential. So the next student gets the next number. It doesn't really matter what the number is. Its only purpose is identifying. Now, why do we need a field that will uniquely identify a member of an entity? We need it to relate entities together, right? Because what are called foreign keys this is how we connect two entities together, or two tables together. So, for example, let's go back to the one that I've sort of been half using as an example, and let's go in and let's make it a little more formal. Let's say I have a project table. And maybe I have a project ID and maybe a name of the project and a description of the project and my estimate of how many hours it will take. That project ID might be related to a customer. Who has a primary key of customer ID. Again, a generated number. That customer might have a name, address, city, state, zip, and maybe some other fields or attributes. We have to be able to point this project to the customer that the project belongs to. All right? The rule in relational databases is the only way you point two entities together is via their keys. So you will take the primary key of one table and make it an attribute in the other table, and that table then, that entity points to that entity. And you define it as a foreign key. Now we'll look at access at some point, and we'll see how to define a foreign key in there. it's not just that we call the field the same name. In other words, it's not just that we call customer ID here, customer ID there. We have to actually go in and deliberately say that we want to make it a foreign key and that we want there to be referential integrity. What does that mean? That means that there cannot be a project that doesn't have a valid customer associated with it. And it doesn't matter who writes the code. All right? If I go through some sort of utility, database utility, or if someone else goes through a web application or someone else goes through a Java application, it doesn't matter. Everyone accessing the database effectively is going through an intermediary, the DBMS, which stands for Database Management System, and they make requests to this database management system, and the database management system actually goes and accesses the data. What does that mean? That means that all the constraints, all the rules concerning good data, including these referential integrity constraints, only have to be implemented in one place. That means that it doesn't matter how any of these applications try, they're not going to get it past the DBMS, because the DBMS enforces referential integrity. If we can take a second to contrast that to how it was with file systems. With file systems, each app accessed and manipulated the file on its own with no intermediary. So, the problem with that is there's still rules, all right, as far as I could still define some rules that, gee, a project has to have a customer associated with it and so on, but those rules would have to be enforced in every application. Then you're at the mercy, again, of your worst programmer, because maybe two of them get the rules right, this one gets it wrong, all of a sudden you have bad data here. Here it doesn't matter who gets it wrong. You're not going to get it past the database and you're not going to have bad data. The only way there could be a potential problem is if this database is not defined correctly. Hence our whole issue of spending a lot of time on the design to make sure that it's correct. There are three ways in which database tables are related to each other, or can be related to each other. Now the interesting thing is these three ways kind of collapse down to one way with a handful of exceptions. All right? I assume, by the way, that this is all review, and I assume that this is beneficial. If this is dreadfully boring for you, if you got all this down, please somehow indicate to me. I won't take offense, honestly. All right? But I do think it's worthwhile to talk about this. There's three ways in which entities or tables in a database can be related, and that's called the cardinality of the relationship. And we can go, there's a little more detail. Some people like to go and talk about it in a little more detail in this, but basically it boils down to one of these three things. There's either a one-to-many relationship, a one-to-one, or a many-to-many. Now, I said that we have these three, but it's sort of, after you shake everything out, have one with a couple of exceptions. Why is that? One-to-many relationship is the one that we're going to end up with. All right? One-to-one relationships are actually kind of rare in databases. They exist, but they're kind of rare. Lastly, many-to-many relationships, you actually can't implement a many-to-many relationship directly in a relational database. So you end up breaking down a many-to-many relationship into two one-to-many relationships, like this. So the many-to-many, you can draw it on your diagram, that's fine, but when you go to actually implement it in the database, you have to transform it to something that looks like that. Now, let's talk about these three kinds of relationship and when you're likely to encounter them. The first one, probably the most common, especially when you consider that many-to-many get broken down into these, is the one-to-many. And the way you read these crow's feet thing is that this is the one side, that's the many side. Sometimes people actually write that there. There's a lot of different slight variations for the notation. I'm not obsessive about notation as long as the meaning is clear. So something like this indicates that there's a one-to-many relationship between this and this. All right? Now, in this case, the one that we've been looking at, the one-to-many relationship was between customer and project. And the way that you identify the cardinality, I kind of gave away the answer and said it's a one-to-many, but if we didn't know there's a one-to-many, you have to look going in both directions. In other words, one customer can have how many projects associated with them? Well, they could probably have many, right? You know, depending on the particular situation. You know, if we did a project for one customer and they came back 6 months later, we're probably not going to say, no, we're not going to do another project for you, right? Even if they had two projects going at the same time, we're probably okay with that. All right? So, one customer can have many projects associated with them. Now, here's the key. Going the other way, we have to examine two. A given project is only for one customer. All right? So that's why this is a one-to-many relationship. All right? Now, the good thing about one-to-many relationships is the way you implement them is very mechanical. All right? Let's assume we have a customer ID and a project ID in these tables that are both their respective primary keys. The way you implement a one-to-many relationship is the entity on the many side has as a foreign key the key on the one side. So in this case, the project, which is on the many side, has an attribute, which is the customer ID that points to the customer table and points to the customer's customer ID. If you think about it, this makes sense. All right? Let's imagine I'm the customer and you're the projects. All right? I'm a customer and you're the three projects that belong to me. Can I point to all of you at the same time? No, I can't. I can only point to one. So I can't point, the customer can't point to all their projects with a single attribute in the customer table. Now, the projects, can you all point to the customer that you belong to? Yes, you can all point to the customer that you're associated with. So the many side can point to the one. Another way to say that is we're going to have a foreign key in the project table to the, that goes to the customer ID in the customer table. All right? So that's how we implement that. And it doesn't even matter. It doesn't matter if we know what those tables are, right? They can be written in code. Let's say this table is the XYZ ABCYC table, and its primary key is that. And this is the 5719B2 table, and its key is this. How do I implement that? Well, I put in the many side a primary key of the one side, and I create a foreign key relationship between those two. So it doesn't matter if you even know what those things are. You implement it, which is good. That's a very mechanical thing. So it may be tricky at first, and this is one thing that I think for the 143 students is tough at first, But the comfort is once you start doing a few of these, you see that really they're all the same. They all work sort of the same. All right? Now, that's the most common one because, again, we're going to find that many-to-many you can't implement in a relational database. One-to-one relationships are rare. One-to-one relationships, there's two kinds of one-to-one relationships. One is called an entity subtype. And one, I guess, would just be a genuine one-to-one relationship. For example, if we weren't considering, let's say, past history, if we were just considering the current situation, and we had a relationship between head coach and football team. Right? Every football team has a head coach. Right? No tag team coaching. And every head coach only coaches one team. So someone doesn't coach the Browns and the Steelers. All right? That would be messy. All right? So that's a true one-to-one relationship. And really, these are actually fairly tricky to implement. What you would have to do is you would have to, if you were going to implement this in a table, you could do this a couple different ways. But you could establish this as a foreign key, and you'd have to specify a unique index. What's a unique index? By unique, it means that a value can only be in there once. And by an index, it means that it's sort of a quick way to look things up. So that's what would make this different from a one-to-many relationship. By slapping a unique index on there, we couldn't have a team or a coach that was pointed to by two teams. Because if coach number 1, 2, 3 was there for the Browns, by virtue of the unique index, coach 1, 2, 3 couldn't be there for the Steelers. All right? These are relatively uncommon. All right? If you think around the school here at Lorain Community, you'd be hard-pressed to really think of a true one-to-one relationship. About the best I could do is between dean and division. All right? If you had a separate table for deans and you had a table for divisions. Each division only has one dean, I think. All right? I know it's always been that way. I don't know if it's a rule, though. It might be that you could have co-deans. I don't know. Maybe it just hasn't happened yet. And likewise, a dean typically is only the dean of one division. All right? Someone isn't the dean of the business division and engineering. They're one or the other. Other than that, you'd be hard-pressed to think of a true one-to-one relationship in the context of a school. They're just not that common. At least these kind of one-to-one relationships aren't particularly common. There's another kind of one-to-one relationship, though, that is different than that. And that is where you have what's called an entity subtype. All right? An entity subtype is like this. Let's say we have, at our school, students and international students. All right? International students, if you look around, on occasion they'll have people in from other countries, coming to our school and taking classes and all that. There's liable to be some different pieces of information that the school requires for an international student. They need to know what country they're from. They need to know what their visa is. They need to know a visa number, maybe the expiration, and so on and so forth. Now, those are attributes that only international students need. U.S. students don't need those attributes. U.S. students don't have a visa. U.S. students don't have a visa expiration, therefore, and so on. So international students are students, but they're a different type of student. And what's relevant in the case of a database is when I say they're a different type of student, they have a set of attributes that the other group doesn't have. So in that case, you can define what's called an entity subtype. Whereas students are in this table that have a one-to-many relation, a one-to-one relationship with an international student info table. And this kind of one-to-one relationship, both tables have the same key. And the student table then would have the fields that are common to every student. Whereas the international student information table would just have those fields that are unique to international students. So an international student would have a row in each of those two tables. Would have a row in the student table with just the generic student information, but in the international table that also have a row with the stuff that's the characteristics of an international student. Now, by definition, this is a one-to-one thing, right? Because an international student isn't going to have several visas from different countries and so on. They're going to have one visa and just one piece of information. These are a little more common in the other kind of one-to-many relationship, but a lot of times people cheat. How do you suppose you would cheat if you were a database designer? How would you cheat in this case? Put it all in one table, right? You could, for example, put in the students table the visa type, the visa expiration date, and so on. What's wrong with that? Well, what's wrong with that is then I'd have to make them optional fields, right? Because for some students, for U.S. students, they're not going to exist. For other students, however, they would exist. So I would have to make them optional. These fields aren't really optional, right? If you're an international student, they are required fields. If you are a U.S. student, you will not have values for those fields. So it's not like other optional fields that you might have, like middle initial, or email address, or something like that. All right? Those are truly optional fields. Anyone may or may not have those. These really aren't optional fields like that. They're optional in the sense that not everyone's going to have them, but there's a rule that says who has to have them, who doesn't. So the purest database designer would say that that is the proper way to implement it. You make then these fields required in that table, and you have a one-to-one relationship to the student table, and an international student will then have both those things in there, both records in both tables, whereas a U.S. student would only have in the one. Now, how would you guarantee that that happened? That's an interface issue. All right? One thing many of my students in the 143 class, and sometimes in this class, get a little confused about is they start thinking ahead, how am I going to develop a form to allow the entry of this? Or how do I, how am I going to make a report that's going to show this, or any of that? That's not our job at this point. When we're database designers, our job is to figure out what the proper way to store the data in the database. By proper, I mean avoiding duplicated data, following the rules for good database design, that is normalization, and so on. That's our job. We're not thinking about how we're going to create a data entry form to allow someone to enter in student information. Now, someone's going to have to think about that, and that someone's going to be you in a couple weeks, but that's not the problem at hand now when you're designing the database. Yes?
Then considering that at this level of creation, do you not want to worry about tools that you can use in the database itself?
What?
Formatting fields, etc.
You'd want to get, you would want to get the data types correct, but anything that was user interface-ish, like I want to show commas in the dollar amounts, or I want to show the phone number as, parentheses around that, I wouldn't worry about on the database level. That's a user interface thing. I would worry about that on that level. So, in the grand scale of things, making this one table isn't good, but it isn't horrible. All right? And that's why you don't see a lot of these, because a lot of folks would cheat in that case. All right? Just simplifies things a little bit, and we'll take the hit on the theoretical downside of that and build some constraints in our application. Now remember, anytime you have a choice to build a constraint in the application or build a constraint in the database, the theoretical best choice is to build it in the database, because that's one place that you have to get it right. Whereas if you build it in the application, every place that uses that, there's a potential to get it wrong. All right, the last example that we're going to look at is an example of a many-to-many relationship. And that's where you look at an example where entities, there could be many on both sides of that. Continuing the project example, let's say we had a relationship between project and consultant. So I have my little consultant company, and right now we only have 3 tables. We have a customer table, and the relationship between customer and project we identified as being a one-to-many. That is, a customer can have many projects, but a given project is only for one customer. Now let's look at the relationship between project and consultant. Now, to be sure, this is where we would have to, find out the way the organization worked. Maybe some organizations, truly, if you're working on a project, you're dedicated to that project. But typically that wouldn't be the case. Typically it would be, you're working on whatever projects we need you on, so you might work on 2 different projects over the course of a day. So, in other words, if we're going to look at this in terms of relationship, one project may have several consultants working on it. All right? And a given consultant might be working on multiple projects. So that's an example of a many-to-many relationship, and these are pretty common. All right? It is pretty common, a common occurrence to see this. However, that can't stand. That can't stay that way when we go to implement it to a relational database. We have to break it down into 2 one-to-many relationships. And we have to add what's called an intersecting entity or an intersecting table. So the way we would break this down is we'd do something like this. We could break that down, that relationship, many-to-many relationship between 2 entities, and make it to 2 one-to-many relationships between 3 entities. This is a project table, this is the assignment table, and this is a consultant table. And there's a few ways that we could do this, but let's look at probably the most straightforward way. If the key to this was project ID, and the key to this was consultant ID, the primary key to assignment, the assignment table, would be a combination of the project ID and the consultant ID. I don't know if I mentioned it before, but a primary key doesn't have to be just one field. It can be a combination of fields, as long as the combination is unique. And as long as both fields are always there. In other words, I could not have in this table a project ID and a null consultant ID. There has to be values for all parts of the primary key. Now, what does that mean? That means that I can have a project multiple times as long as I have different consultants. Or I can have a consultant different multiple times as long as it's for different projects. Typically, this is the way I go about designing databases. I sort of take what I guess you'd call a top-down approach. I think in terms of the main entities, the relationships between the entities, and then fill out the attributes you need. So in this case, what do I need to know about a project? What do I need to know about a consultant? And so on down the line. Trying to think if there is anything else I want to say about this example. Any questions at this point? Sure. Okay.
Oh, with that international student and student.
Yes.
Talk about keeping, right?
Right.
Keeping in one database.
Not in one database, but in one table.
One table.
Right.
Yeah, one table. And not all students has those information.
Right.
It's going to be a null field.
It'll be a null field. Right.
Would that be counted as the size of the database?
Not really.
The size of the table.
Not really. The null fields would not have a substantial effect, if anything, on the size of the table.
When it comes to the database.
Yeah.
On a file,
Yeah. Right.
it is.
Because it's not actually a null. It's spaces.
Right.
Yeah. So. Yeah. I would not think the bigger. Again, I guess it would depend on exactly how the database is implemented. But the biggest issue wouldn't be the space that you'd take necessarily. It would be the fact that you would have to make those optional. So I could go and put a U.S. student in with a visa in there, and that's not proper. Or I could put in an international student that didn't have visa information, because I have to make those fields optional. All right?
At least the null field is not counted.
Yeah.
I'm thinking about the cost.
Yeah, you would have to know specifically how the database implements it. I would not think that would constitute a significant thing. It might add some space to it, but it probably wouldn't be a significant amount of space. Yeah. All right. Here's what I want to do. I'm going to define a problem for you, and you can spend the remainder of today working on it, and you can work on it together if you want, or you know, work on it in pairs and threes and however I want. You can ask me whatever questions. I want to describe a scenario, and I want to develop a data model for this, you know, an entity relationship diagram. These are called entity relationship diagrams because they show entities and their relationships and their diagrams. All right, so ERD. So we'll develop that for this scenario, and you can start it now. If we have 20 minutes left in lectures. Take those 20 minutes, then we'll hit the lab. All right. You're certainly able to work on it after lecture today if you want to. Then we'll talk about it on Thursday to start off on Thursday. And here's the example that I want you to go. I want to develop a relational database for a college bookstore inventory. The fancy word for this would be the problem domain. In other words, another way of putting it is that it's what's relevant to our problem. We're interested in keeping track of the inventory. We're not keeping track of the stales that the bookstore has or anything like that. All right. College bookstore obviously has books. All right. Those books can either be new books, used books, or they can send you a code to download they can sell you a code to download an ebook. So essentially they can sell you a new book, an old book, used book, or a ebook. Books are used in classes. Classes have multiple sections associated with them. In other words, there is, for example, a class section of CISS243 and an online section. For some classes, there's a day and an evening class. All right? Each section is taught by a professor. All right? It might be that the same professor teaches all sections of a class, but it's not necessarily the case. For example, 143. This term I teach the online section, and other people teach the day and evening sections, probably Mark Harms. All right? A good, very good adjunct, in my opinion. So it could be that one professor teaches all the sections, but not necessarily. Now, there can be, the choice of books is up to the professor, whoops, that teaches the section. Again, this is a hypothetical. This isn't how it is here at LC. At LC, for the most part, the same course has the same books, but I wanted you guys to have even more fun, so I complicated the problem a little bit. So, the professor that teaches a section determines the books. There can be multiple books for a section. And the last rule is all of a professor's sections for a class uses the same books. I think these are fairly realistic assumptions. In other words, I wouldn't for my online class have a different book for CISS243 than I have for my campus section. I want you to develop an ERD for this. We will, again, take the rest of the time today. You can work on it after, on your own time, and we'll discuss this on Thursday. All right. We'll stay here until the class is done at 6:30, and then we'll move up the lab.